In this video, I'm going to cover section 12.1, the last section that we'll be covering this year. Some vocabulary that you're going to see: sample regression line, population regression line. This acronym LINER we're going to use when we look at conditions, standard error of the slope, and a one sample t-interval and one sample t-test for the slope. So we've done a lot of interpreting in chapter 3.2 of y-intercept, slope, standard deviation of the residuals, and r squared. We're going to look at one more interpretation in this lesson, the standard error of the slope. Let's kind of just jump in looking at what this is going to look like. So I'm actually going to flip on to page 2. So when we calculate a least squares regression line, we're trying to estimate a slope and a y-intercept. The slope is, the sample slope is denoted by lowercase b. That's the statistic. And the parameter, or the population slope, is denoted by beta. So we would have talked about how to interpret the slope and y-intercept back in lesson 3.2, the standard deviation of the residuals, same thing, and the coefficient of determination, that should be 3.2. Now the standard error of the slope, that's not something we discussed in that lesson, so I'm going to show you the interpretation here now. This is going to be if we repeat the random assignment many times, that's how much the slope varies from the slope of the true regression line between whatever x and y are in context. And we'll take a look at a specific example here in a minute. I just want to mention other interpretations that you still need to know are p-value in context, confidence level in context. While I'm thinking about it, type 1 and type 2 errors, and power. They could ask any of those follow-up questions for a test. So if we take a look at this check of understanding, they're talking about dropping paper helicopters from different drop heights, and they randomly assigned the helicopters to 5 drop heights. So we have this regression analysis here, and it says give the standard error of the slope and interpret the value. So I have to be able to understand what this table is showing me and how to utilize it to figure out the standard error of the slope. So the constant is the y-intercept. So this value is the y-intercept. The variable in the regression analysis table is going to be your explanatory variable. So the number in front of x, this is going to represent the slope. So this standard error coefficient, this is going to be the standard error of that slope. So the standard error of the sample slope, lowercase b, is 0.0002018. So it's very minute. Interpret the value. So I'm just going to fit it to this interpretation. It was random assignment. This was an experiment. So if we repeat the random assignment many times, the slope typically varies by 0.0002018 from the true slope of the regression line between, in this case, drop height and flight time. Oh, you can't see that, my apologies. So that's just the typical variation between the sample slope and the true slope if we perform this experiment over and over and over with random assignment. So that's an interpretation that you're going to need to know for this unit. Let me move on and take a look at the next part of this lesson. So we're going to take a look at the conditions that you need to check for performing a confidence interval and how to actually do the confidence interval. So if we look at this check your understanding, A thrill seeker wanted to travel across a large field while being suspended in the air by holding onto balloons. In order to determine the number of balloons needed, he did a preliminary study. He does a random sample of 20 rocks of various sizes, weighed each one, and figured out how many balloons are needed to lift the rock. Here is the output. So, part A, construct and interpret a 90% confidence interval for the slope. So I'm going to set up my state plan do conclude. As we've seen in the past, the state step is just going to involve defining the parameter. I mentioned earlier in the lesson the true slope is beta. So this is going to be the true slope of the population least squares regression line relating weight to number of balloons. That's it for the state step. The plan step. I had mentioned that we're going to use this acronym LINER, L-I-N-E-R, to help us with our conditions. And that's exactly what we're going to do. L is going to be linear. So there's a few plots that we've seen before. I just want to reintroduce them. This is the scatter plot. The middle one is the residual plot. Just a reminder on the residual plot, that line at 0 is your least squares regression line. So in order for a linear model to be appropriate, two things need to be true. The scatter plot needs to be roughly linear, and the residual plot needs to show no pattern. So I need to mention both. I'm just going to abbreviate scatter plot SP right here. Scatter plot is linear, and I'm going to abbreviate residual plot RP has no pattern. That's it. I stands for independent. We're sampling without replacement, so we're going to be checking the 10% condition, which we've done quite a bit. 20 is less than 10% of all rocks. N stands for normal. We've checked the normal large sample condition. 20 is not a large enough sample, so what we do here is we take a look at, in this case, the dot plot of the residuals. It could be a histogram, a stem plot, a box plot. And just like we did with the box plots, we're looking for no strong skewness or outliers, and we don't see that. Dot plot shows no strong skew or outliers. E is going to represent the equal standard deviation. And for the equal standard deviation, I'm looking at the spread of these residuals. I do not want to see something that is cone-shaped, where I start out with maybe small residuals and I'm getting larger and larger residuals. I don't see that here. When I again abbreviate residual plot, don't do that on a test or the AP exam. I'm just trying to save a little time here. Residual plot shows consistent variation or variability. And the R in LINER stands for random. And this was a simple random sample of 20 rocks. So our conditions are met. We're going to do a one sample T interval for the slope. The degrees of freedom are calculated by taking your sample size minus 2. That's a little different than it's been in the past. It's been sample size minus 1. The reason it's minus 2, we're estimating both the slope and the y-intercept. So we have two parameters. So it's n minus 2. On to the do step. This has the same structure that every confidence interval we've done has had. So taking the formula sheet here, it's your statistic plus or minus your critical value times your standard error. So your statistic on your formula sheet is B, the sample slope. So I can get that right from the regression output. There's my sample slope. And there's the standard error of the slope. So I have two of the three things that I need. So it's going to be 30.4126 plus or minus. Critical value, if I want 90% confidence, that leaves 5% in each tail. and 18 degrees of freedom. So that's going to result in 1.734 times the standard error of the slope, which I'm getting right from the table. Adding and subtracting the margin of error to our point estimate, we end up with 26.87 to 33.95. And the conclusion, similar to what we've been doing here, we are 90% confident that the interval from 26.87 to 33.95 captures the true slope of the population least squares regression line relating weight to number of balloons. So that's part A. Part B, explain the meaning of 90% confidence in context. So that's your confidence level. So part B would be, is this a random sample? Yes. If the sampling process were repeated many times, about 90% of the resulting confidence intervals would capture. And then it's going to be the same exact context here. I'm just running out of space. All right, that's the first part of the lesson. Hopefully it made some sense. I'll be back in a minute with the second part.